Welcome. In this session, we'll explore the second derivative extension from scalars to vectors, and we'll look at the Hessian matrix, which is the second derivative equivalent. So let's recall for scalars what we had. Recall that if a function had a scalar argument that was mapped to a real level, that T star is a minimizer, and that occurred wherever the second derivative at T star was strictly greater than 0. That is, T star had to be a stationary point. This doesn't apply at anything other than a stationary point. So if a stationary point was a minimizer, that meant that this was convex. That is, it was pointing upward. Now, what we have to ask ourselves is, what's the second derivative equivalent? Well, let's go through this in little pieces, right? So in scalars, the derivative of a function is the rate of change of that function. And let's recall, this is important, let's recall that this is a function also. That here, ddt is an operator. That is, it's something that takes a map in and it produces a map out. So this is a map of maps in some way. We call it a linear differential operator. And the result is that f prime is itself a function. And because f prime is itself a function, we could define the second derivative as the rate of change with respect to the scalar argument of the first derivative. And we could even put parentheses around that to be utterly clear that what's inside those parentheses is a function. Now, what can we do in scalars? Sorry, in vectors. So let's consider a function that has an n-dimensional vector argument and produces a real level. The first derivative is the gradient 1 form. And the gradient 1 form at any w was, we would take the derivative of f with respect to component 1, evaluate that at w. Subsequently, I'll drop these evaluate at w. For now, let's keep doing this. So the partial derivative of f with respect to component 2 evaluated at w, and so on, and the partial derivative of f with respect to component n evaluated at w. So that was our gradient 1 form. How can we differentiate this? Well, one way that can be done is we could just try differentiating this whole thing and we'd end up with, it's not clear what we'd end up with. So the usual way is to define a Hessian matrix. And this is the Hessian matrix of a function. And this has entry hij is defined as the second derivative of f with respect to component I, component j. So that's the usual definition. I think that we could approach this in a different way. Let's try using this idea. So in the second derivative, what we said was we want to take the rate of change with respect to the scalar of a function. Here we have it as a row. So let's consider this. Let's consider, we'll write this, instead of using a symbol h, we'll write this, this is quite common in optimization and calculus, is we'll write this as grad squared f evaluated at w. And what I'll do is I'll say that that is the gradient of, let's take that gradient and let's treat this as a column, that is as a vector, instead of as a one form. So let's say that that is transposed. And what we would get if we did that would be the gradient of, so let's take this transpose first. So we take this first entry, and that will be the partial derivative of f with respect to component 1, the partial derivative of f with respect to component 2, and so on until we get the partial derivative of f with respect to component n. Now, let's see what that would do. Well, the first thing we would do is, back in calculus, we treated the derivative as though it was a function. Here, we can treat this as though it's a function. That is, we can take that original f, and then we can use the rules of calculus to find the partial derivative with respect to component 1, and that would give us a new function. And if we differentiated f with respect to w2, in general, we're going to get a different function. So this function and that function are different. And when we developed the Jacobian matrix, we said we were going to take each one of these functions, and then we were going to find its gradient. Well, we can do that again. A little notation problem is what of these comes first. And let's recall from elementary from multivariate calculus, let's recall that the second derivative of f with respect to, if we do I of the jth version, that is the same as the partial derivative of f if we did j of the I version. And because of this, the Hessian matrix means entry ij is entry ji, and that means it's a symmetric matrix. So now I can see ahead, I can see, oh, I'm going to be building a symmetric matrix. With this, it says I can write these entries in whichever way is most convenient for me. So the way I'll write that is, let's start processing this. So if I take the gradient of this, so that this is a function, right? If I take the gradient of this with respect to 1, that is the second derivative of f. We take 1, and then we take that with respect to 1. The second entry of the gradient of the derivative would be, now I would normally write w1 here and then w2. To make it a little clearer that I'm dealing with a matrix, I'm going to reverse those. And I'm going to say that using this rule is the same as doing 2 and then 1. And I can continue filling this row until I get to the end. And here I should have 1 and then take the 1 and then do it with respect to n. Now I'll use this property and say that that's 1n. I can then process this entry. So that is the second derivative of f. I'll apply this rule again, and that is 2, 1. This entry is 2, 2, and so on. This entry is 2, n, and I can carry on until I get to my last entry here, and its gradient is the second derivative, and now I'll transpose and make that n1, second derivative, commute. I shouldn't have said transpose there, I should have said commute. So commute n2, and the matrix is completed with the second derivative with respect to n. So here, this gives us a matrix that equals its transpose. So it's symmetric. Now I can see that this definition and this definition are the same.